So friends, now we will discuss that how the heating done by microwaves is different from the conventional heating. So as you can see in this diagram on the picture above, on the left hand side, you will see that it is the conventional heating, and this conventional heating is largely done by the mechanism of conduction, wherein we heat the material from outside and gradually the heat travels toward the central core of the substance, and as a result of heating, the content or the mass that is present in that cell, it flows outside. So we can say that the direction of heat flow and the mass flow are opposite in conventional heating, whereas in case of microwave heating, we have discussed that the substance tend to absorb the microwaves, and these absorbed microwaves lead to the heating effect. So you can see on the picture on the right side, the central core is heated, which is shown by the red color. So microwaves are absorbed and the central core gets heated, and the heat starts dissipating towards outside, and once the cell is ruptured, the mass flow or the content flow also occur toward outside the cell. So we can say that in case of microwave heating, the direction of heat flow and mass flow are same, that is toward outside the cell from the center, whereas in case of conventional heating, the direction of heat flow and the mass flow are opposite. Heat flows from outside to the central core and the mass flows from the inside towards the outside the cell. The second graph shows you the consumption of the power during an extraction process in comparison to the oil bath or the heating mantle. So we can clearly see that the power consumed by the microwave in an extraction process is significantly low in comparison to the oil bath or the heating mantle, which are nothing but the equipments used for the conventional heating mechanism. So this is one example how the microwave heating differs from the conventional heating. Now we move on to instrumentation of microwave assisted extraction. Now before we move on to different components of the microwave assisted extractor, there are certain points that one has to keep in mind while designing an microwave assisted extraction. So first one is the homogenized distribution of electric field, and one has to keep in mind that whatever type of microwave reactor he or she designs, it should allow a homogenized distribution of electric field into the cavity, and this can be achieved by introduction of stirrers or by rotation of the extraction vessel itself. And when we will how this rotation happens, we will discuss further when we will discuss about the microwave extractors or their components. Then the second point that has to be kept in mind is the penetration depth of microwave. As we discussed that the heating of microwaves is also dependent upon the penetration depth of the microwaves into the object. So we have to design the reactor in such a manner that the penetration depth of the microwave should not be affected. No matter how large or how big microwave extractor or reactor we design, penetration depth should always be considered before designing the size of the reactor. Next thing which has to be kept in mind is the temperature and pressure. Now there are microwave reactors which operate at atmospheric pressure, and there are microwave extractors or reactors which operate under pressure above the atmospheric pressure. So in such cases, one has to be very careful while designing the microwaves in order to control the temperature and pressure. Even if you are working at higher pressure, you have to design a reactor in such a manner that increased pressure or temperature should not have any kind of safety issues. Then the reactor spare parts cost should also be considered. It should not be that we have designed a microwave reactor and its repair or the spare parts are too costly to repair the microwave, which will increase the overall cost of the extraction process. So again, cost factor should always be kept in mind. And last but not the least is the safety aspects. So whenever you are designing a microwave reactor or a microwave oven for extraction, then one has to be very careful that there should be no leakage of microwaves. If you are using a closed system, you are working at a higher pressure, one has to be very careful that increased pressure or temperature condition should not affect the user which is using the microwave. So these are few points one has to consider while designing a microwave reactor apart from other technical details. Now we move on to the components of the microwave, and these components are magnetron. As I told you, magnetron is the heart of the microwave. Then transmission lines or the wave guiders which guide the microwaves towards the cavities. Cavities are the open areas where the extraction vessels are kept. Second is the cavities we have discussed. Next is the extraction vessels. Extraction vessels can be open vessels or the closed vessels. Open vessels are those which work under atmospheric pressure, and closed vessels are those which can operate at higher pressures. Then temperature and pressure sensors to keep monitoring the rise in temperature or rise in the pressure during the microwave assisted extraction or any kind of reaction that is being carried out using microwaves. So starting with magnetron. So as I told you, it's the heart of microwave, and it is the equipment that is responsible for the generation of microwaves, or it produces microwaves. Now, as I told you that most of the industrial, scientific and medicinal uses have been restricted to a frequency of 2.45 gigahertz. So majority of the microwaves which are meant for industrial, scientific or medicinal uses, they have a magnetron that emit microwaves of this particular frequency. And these magnetron can be of different types, and the most primitive type is the conventional vacuum type, followed by its development single anode. Then we had split anode, and cavity anode are the latest one which are most widely used nowadays. Now the above two, conventional vacuum tube and single anode magnetrons, they had a problem of overheating. Now to overcome this overheating problem, split anode magnetrons were developed, wherein they had two anodes, or the anode was split into two, which work alternatively to produce the microwave. So if one anode gets heat up, the second start working. But again, this type of magnetron were having several other problems which led to more efficient and more modern magnetrons, that is the cavity anode magnetrons. Now as you can see in this picture, cavity magnetrons or cavity anode magnetrons have structure something like this, and on the picture on the right you can see there is a yellow cylindrical structure. This is nothing but a cathode, and this cathode is surrounded by a red color or orangish colored anode. Now whenever, and you can see that anode has certain cavities in it, and that is why the name cavity anode magnetron is given. Now whenever electric or magnetic field or microwave electric field is applied to the cathode, electrons, they bounce and they move towards anode. This is ionic conduction. Now if we observe this phenomena under normal conditions, then the electrons that bounce off cathode on application of electric current, they will move in a straight direction towards the anode. But in case of magnetron, there are two conditions that have been changed. One, we place a magnet below the anode, which you can see in a picture on the left. And second major change done was the introduction of the cavities in the anode. Now whenever electric field is applied, the electrons bounce from cathode and move toward anode. But due to the presence of magnetic field, which is produced by the magnet present below the anode region, the electrons start moving in a circular fashion. And when they move in the circular fashion, since cavities are present on the circumference of the anode, these cause the resonance by the electrons, and this resonance leads to the generation of microwaves. So this was in brief how the magnetron produces the microwaves. So whenever electric field is applied, the electrons from the cathode bounce towards anode. Due to the presence of magnet below the anode, there is a magnetic field. So these electrons move under the influence of electric as well as magnetic field in a circular fashion. And when they move in the circular fashion, they pass through the cavities, which leads to the resonance effect. And this resonance effect or the resonating electrons, they produces the microwaves. And these microwaves are then directed with the help of wave guiders to the cavity. Now cavities, depending upon how the microwaves are applied on the sample, can be single mode cavities, which are also known as mono, or more popularly known as focus mode cavities. Then we have multi-mode cavities and continuous flow cavities. Now the monomode cavities, as their name indicate, they only excite one mode of resonance. That is, whenever the microwaves are produced by the magnetron, they are guided by the wave guiders in a one direction, in a particular direction, and in that particular direction they will enter into the cavity. So they will not be distributing haphazardly, but they will move in a particular direction, and in the cavity they will fall onto the extraction vessel where the sample is there. So the movement of the microwave will be in same direction, and the sample can be placed in the waveguide where microwaves are focused, and that is why these are also known as focused microwave cavities or the focused mode cavities, because microwaves are moving in single direction and they are focused onto the extraction vessel. Now in this diagram you can see how the monomode or the focus mode cavities work. In the left picture you can see the magnetron generates the microwaves, and these microwaves are directed with the help of waveguide in a same direction, and they fall onto the vessel where the sample is placed for the extraction. And the second picture on the right shows you the cross-sectional view of the monomode microwave extraction cavity, wherein the sample which is placed in a vial, a red colored vial, and on the both sides are the microwave guiders which guide the microwave onto the vessel. So this is the simplest example of a monowave cavity, monomode cavity, or the focused mode cavity of microwave. Now there are few advantages of monomode cavities. They are very simple and they are very easy to design. So you just have to take a magnetron and you have to introduce a wave guider which can guide the microwaves onto the sample, and that sample you can attach with the vessel, you can attach with the condenser to avoid the loss of the solvent. And as the condenser is attached, so we can say that these type of cavities are, or the extraction that occurs in these type of cavities are normally at the atmospheric pressure. But yes, there are monomode cavities are also available which work at pressure above the atmospheric pressures, which we will discuss further. So these monomode cavities have higher energy efficiency and well-defined electromagnetic field which can be matched to the reactive vessel geometry and the position. So you can always manipulate the direction of the electromagnetic waves or the microwaves or the efficiency of these microwaves by just maintaining a single direction of their movement into the reactor vessel. So these monomodal cavities provide higher electromagnetic field homogeneity, and since these waves are moving in a single direction and they are falling onto the sample in one direction only, so large homogeneity can be obtained. Now these monomodal cavities are also used as the starting equipments and can be used for scaling up processes. So since they are easy to design and they are simple to manufacture, one can easily use them to scale up. So one can easily start with a laboratory sized equipment. Once the factors are optimized, they can shift on to the pilot scale, and from pilot scale they can shift on to the industrial scale by again optimizing those parameters. But there are certain disadvantages with these monomodal cavities. Usually they are small in dimensions, and since they are small in dimensions, you cannot extract larger amounts of material in these extractors. Arcing and plasma are generated during high electric field. Now whenever electric field or microwaves are moved in a single direction, obviously high electric field will be there, and this kind of high electric field sometimes lead to arcing phenomena, which is nothing but the development of electronic sparks in the electric field. And since large amount of sample cannot be processed in these small monomodal cavities, so per sample cost obviously increases, because you cannot put in large amount of the material into the extraction, thereby you have to expose your sample in batches to complete the extraction process, which increase the overall cost. Now we move on to the multimodal cavities. Now as their name indicate multimodal, it means the waves do not travel in a one directional manner. So radiation is allowed to disperse randomly in the cavity and the sample it contains is evenly irradiated. So you can see that magnetron picture on the left, you can see magnetron produces the microwaves. These microwaves with the help of waveguider are subjected towards the cavity where they are randomly dispersed, and in the cavity is the extraction vessel. So in the monomodal cavities we have the microwaves traveling in one direction, whereas in case of multimodal cavities these microwaves travel in multi-directional manner. So on the right you can see a simple laboratory multimodal cavity extractor by Anton Parr. This picture on the left will show you how you can obtain homogenized distribution of microwaves. So you can clearly see the extraction vessel that is present in a multimodal cavity of the microwave is continuously rotating. Now this principle you always observe in the domestic microwaves also, which are nothing but the multimodal multimodal cavities, wherein the tray that is on which we place the food, it keeps on rotating. Now this rotating basically helps in homogenization of the microwaves across the samples. And on the right side you can see a 10-liter reactor, which is a pilot or a scale-up sort of multimodal reactor. Now there are certain advantages and disadvantages of these multimodal cavities. So advantages are they are easy to construct and have large dimensions. So as you can see, there is a 10-liter reactor, that microwave reactor that is being used by the industry. So you can easily set up, you can easily make up the large equipments in case of multimodal cavities. Possibility to homogenize the electromagnetic field rotating devices is possible. As we have seen in this picture, the extraction vessel, it keeps on rotating into the cavity. So as I told you that this helps in homogenized distribution of the electromagnetic field. Then they have a possibility of installing multiple microwave inlet ports. When you are making big microwave for industrial or pilot scale, then you must have multiple microwave inlet ports. And since these are multimodal cavities, random distribution of microwave is there, you can always have multiple microwave inlet ports, which also increase the extraction efficiency and reduce the overall time that is involved in the microwave extraction. And these are considered to be relatively inexpensive. The major disadvantage in the multimodal cavities is, as I told you, that we can make larger microwave reactors which work on the principle of multi-mode distribution of microwaves. But as we increase the size of the microwave generators or the microwave reactors, we can compromise on the penetration depth of the microwaves. So this is the major drawback. So one has to be very careful if you are designing a multimodal cavity of larger size. One has to take care about the power penetration depth of the microwaves. We should not compromise the penetration depth of the microwaves with the increase in the size of the reactor. Now both these cavities, whether it is a multimodal or a monomodal or the focused modal cavity, they are widely used but cannot be scaled up simply by using the large reactor. So one reason I discussed that you cannot just scale up the multimodal cavity by just increasing the size of the reactor. You also have to take care about the penetration depth. Same is in the case of monomodal cavities. We cannot scale up just by manufacturing a large reactor, because of the same reason penetration depth of the microwave into the absorbing target is reduced. As you increase the size, the penetration depth decreases. So one has to be very careful. So if the extraction is carried out under high pressure, there can be significant danger of the reaction vessel undergoing multifunction and or malfunction and or rupture. So if you are using a closed vessel or a multimodal cavity or a monomodal cavity, then if you are carrying out your extraction process at pressure above the atmospheric pressure, which is largely helps in keeping the solvent into liquid form even above its boiling point, but one has to be very careful in monitoring the pressure and designing such an equipment that it can withhold the high pressure that is being utilized for the microwave extraction. Third category of the cavities is the continuous flow cavities, and these cavities because the major drawback of the other two cavities in comparison to continuous flow is you have to extract the sample in small batches. In monomodal cavities, you have to take small sample to extract out. In multimodal cavities, you can increase the amount of the sample because you have different extraction vessels in it. Thereby, you can increase the amount, but you cannot continuously extract it. You have to stop the extraction process. You have to discharge the exhausted material. You have to fill the extraction chambers with the fresh material. Again, you have to start the extraction. Whereas in case of continuous flow cavities, this process can be omitted. You can continuously keep on extracting your material. And this is largely used to intensify the chemical reactions. And we don't require to increase the size of the reaction vessels if you want to accommodate large amount of sample, as we have to do in the case of single or the multimodal cavities. Now this continuous flow cavities also helps in overcoming the penetration depth problem, because we discussed that as you increase the size of focus mode or the multimode cavity, the penetration depth decreases. Whereas in case of continuous flow, since we don't require to increase the size of the reaction vessel, we can overcome the problem of the penetration depth, or we can say there is no such problem of the penetration depth. So in this picture you can clearly see a continuous flow cavity, wherein on the left side we have a hopper which keeps on inducing the solid material into the reactor, and on the right side there is a screw which keep on rotating and removing the solvent, and the solvent is pumped from the left side, and in between the extraction chamber or the cavity they are exposed with the microwaves, and this process continuously keep on going. And the only point is we have to optimize the speed of the liquid flow or the solid flow through the continuous flow cavity. We have to give sufficient time for the extraction in that flow cavity. Now the next component of microwave is the reactors. Now depending upon the pressure at which they operate, we can categorize reactors or the extraction vessels into open system vessels or the closed system vessels. Now monomode or the multimode cavities, they both are available with both these types of open and closed system vessels. But as I told you that open system vessels, they operate at atmospheric pressure, and generally by and large you will see that single or the monomodal cavities, they work with the open system vessels. And since they work at atmospheric pressure, and as I told you microwaves are generally focused in one direction, they are also known as focused microwave assisted extraction. And maximum possible temperature to which a solvent can be heated is its boiling point, because we are operating at atmospheric pressure, so you cannot heat the solvent beyond its boiling point. Now electric field that is generated or microwaves that are produced in monomodal cavities that are using these open vessels, they are homogeneous and reproducible, therefore causing efficient heating of the sample. Whenever you have to open the sample, you open the microwave, a cooling system is required, and this is required just to prevent the loss of the solvent or the volatile matter which is supposed to be extracted from the drug material. And therefore you will see that the open type of microwave cavities or the systems, they always have a condenser attached to them, that is the cooling system attached to them, which prevents the loss of the solvent or the volatile components which you want to extract out. Now there are certain advantages of open systems. You can work at atmospheric pressure, and therefore they are considered safe because no higher pressure is there, so no danger of explosion of the vessels is there. Solvents can be added or excess solvents can be removed during the extraction. Large samples you can process with the open extraction vessels, but again you have to process them in batches. Since they are very simple to design, simple to set up, they have a initial low cost, and they are quite easy to assemble. Now these type of open systems, they are better suited for the thermolabile constituent, because you are extracting the material at a temperature which is equivalent to the boiling point of the solvent, or sometimes even below the boiling point of the solvent. Whereas in case of closed vessel systems, we can, since we are extracting out the material at higher pressure, we can always heat the solvent above its boiling point, and therefore closed vessels are normally not suitable for the thermolabile species. And these open systems can be easily linked with the other steps that are involved in the analysis. When we say that they can be linked with other steps, it means they can be hyphenated with other analytical techniques also. Now, there are certain disadvantages. Method is less precise than the closed system. Now, as the method is open, it is subject to the variations caused by the atmospheric pressure or the temperature changes. So, therefore, the method is considered to be less precise in comparison to the closed system. It has low multiple sample handling. As I told you that the monomodal cavities are largely used for the open vessels, so you cannot use multiple samples or large amount of samples in one go in these type of reactors. Therefore, you have to extract out large material in small batches, which increases the overall cost and has a low sample throughput. Longer durations are required to get results similar to that of the closed system. Obviously, since the method is not precise in comparison to the closed system, there are a lot of variations in terms of pressure and temperature. It requires longer duration in comparison to the closed system. Now we move on to the closed system vessels. Now, closed system vessels, as I told you, that these are performed under pressure, which is typically less than 14 bar, and since they are performed under pressure, these are also known as pressurized microwave assisted extraction. Now, the major advantage of this system is that whenever you apply the pressure, you are allowing yourself to heat the solvent above its boiling point, and therefore it improves the overall extraction efficiency. But this kind of system is not meant for the thermosensitive or thermolabile constituents. And as we have already seen in the picture of a multimodal cavity, multiple extraction vessels are there, and you can accommodate from 6 to 40 extraction vessels, wherein you can place same sample in different cavities, or you can extract different samples in one extraction cycle. Therefore, it has a high throughput as well as low per sample extraction cost. Now, there have been development of these closed vessel extraction vessels. The first generation extraction vessels were made up of PTFE or Teflon, and these samples have a drawback that they cannot handle high pressures, and they have to be operated under low pressures. This was followed by the second generation extraction vessels, which were nothing but the jacketed vessels, which typically consisted of Teflon liner and a cap of polymer case. And these were nothing but the modifications of the first generation. And because they have a jacketed vessel and a Teflon lining, the overall ability to withstand the pressure was increased up to 20 atmosphere. This was followed by the third generation extraction vessel, closed extraction vessels, which were again modification of the second generation. Their structure was overall modified, and they were designed in such a manner that they can withstand the pressures up to 20 to 150 atmospheres. So this was just a brief overview how the development of extraction vessels took place. Now we move on to the advantages of closed vessels. Since they are a closed extraction is being done in a closed vessel, there is no loss of volatile component or there is no loss of the solvent. And since you can extract at higher temperature above the boiling point of the solvent, less extraction time is required. Vis-a-vis, less solvent is also required. And since everything is closed, the user is not exposed to any leakage of the vapors of the solvent or the volatile components of a particular drug. So the user is quite safe towards these aspects. It also has certain disadvantages, and the first disadvantage is it poses certain safety risk. Since we are carrying out extractions at higher pressures above the atmospheric pressure, so one has to be very careful. One has to continuously monitor the pressure at which extraction is carried out. Once extraction is complete, we have to first depressurize before we can commence on to the next extraction. Cooling of vessel is required before opening because it will cause the loss of volatile oil. If you are not cooling the vessel before opening, it will cause the loss of the volatile solutes. Then addition or removal of the solvent in between is not possible because it's a closed system. So friend, this was about some of the components of the microwave that are involved in structuring a microwave reactor. In the next lecture, we will continue with the other components of the microwave extractor or a reactor. Thank you.